Welcome to the second video of Discrete Mathematics. In this video, we'll be talking about truth tables. A truth table is a table which consists of all possible combinations of truth values of a logical operation. This is best understood if you actually apply it to a truth table. So we'll be looking at a few in this video, and I'll explain what rules that certain logical operators have so that you can determine the truth value of a logical operation. Here's what a basic truth table looks like. So let's first break down the components of it. For every proposition in a logical operation, you need to make a column for it. If there's a R, you need to make a column for R as well. Now, since there's only two propositions in this, these are all the truth values, the combinations that we're going to get. If we had a third proposition, this would be 8 rows long. But since we only have two, we have true, true, false, false, true, false, true, false. This is the setup for a truth table for two propositions. So now, how do you use a truth table? How do you figure out the truth values that go in that column? So first we need to look at the logical operator between the proposition. That's the or. That's the disjunction. And that operator says that if this or this is true, then my statement is entirely true. So just one of them has to be true and the entire thing will be true. So it has to have at least one true. That means that this is true, this is true, this is true, and the last one is false because neither P or Q are true. And that's basically what a basic truth table looks like. After you make a column for your propositions, you have to make one for the entire logical operator. Now let's make a truth table for the logical operation of negation of P and Q. I would like to make a little disclaimer. Always make a column for the negation of a proposition. I've seen many people make the mistake of trying to do it in their head because they have a column for the original. Just make a column for the negation. You're bound to make a mistake by accidentally using the actual truth value, and you're going to get a completely different result. It doesn't hurt to make an extra negation column for a proposition. I even once saw my professor make that mistake, so just make sure not to make it. So we have the column for P, the column for Q, we have the column for negation of P. So true, if we have two trues here, we have two falses here, then two trues here. Now, our logical operation only consists of Q and negation of P. So this is all we have to look at now, once we find the values for both of them. Which means that we no longer need this column. I'm not saying don't write it if you see negation of P and stuff, but just like once you write this and then find negation of P, then you can just not look at P. So now let's see what truth values we can find for negation of P and Q. You're only comparing truth values in this. Just don't care about the letters of the proposition or whatever. Don't let that confuse you. All it's saying for the conjunction operator, the and, is that if this and this are true, then my statement is true, otherwise it's false. If it has even one false, then this and this aren't true. This and this aren't true. And is the key word here. So, true false gives us false. False false obviously gives us false. True true gives us true because this and this are true. And lastly, false true gives us false. Now, we move on to something bigger. By the way, this is what we did in the first truth table. These are the exact values we got to. So, we have our basic setup, 2 columns, one for each proposition that is in the logical operation. Now we have to break it apart. Whatever's in this pair of parentheses, whatever is in this pair of parentheses. I remember we did this in the last video, where when we had to put it into a sentence, we broke it apart. We have to look at the connector last. That's what connects this proposition that's on its own and this proposition that's on its own. I also mentioned in the last video that everything in a pair of parentheses put together has its own truth value. This entire thing has its own truth value, and that's what we're seeing over here for P or Q. It has its own truth values, P or Q put together. So that means that P and Q also has its own truth values that we can find. So P and Q, the simple rule goes, if they're both true, then P and Q is true, or else it's false. So this is true and this is true, so that makes this true. And then this is true and this is false, that makes it false. This is false, this is true, this makes it false. False, false makes it false. Now, we have the two parts of our actual logical operation. So now we only have to focus on these two columns. Those are the only truth values we care about now. Let's try to remember the rule for exclusive OR. It's exclusive to one truth value on one side and one truth value on the other. So it's exclusive to one truth and one false. That means if you have true, true, that's way too many truths. It has to be true, false. Has to be true, false. Exclusive OR means that it has to be one true, one false. It's exclusive to one true. So true, true gives us a value of false for the exclusive OR. True, false gives us true. Again, true, false gives us true. And false, false, again, same truth value, meaning that this is false. The exclusive OR just doesn't allow it. This wasn't as complicated as it may have seemed at first. All you have to do is break it down piece by piece. Look at what's in one pair of parentheses and then what's in the other pair of parentheses, and then just connect it. Just compare the truth values after that. Now we have conditional statements. If P, then Q. So, if true, then true. Logically, I don't even have to explain this. This is just true. If true, then true. If true, then false. I'm gonna have to explain why this one's false, because I'm gonna have to put this in an example. Let's say that I make a bet with you. P is the proposition that pigs can fly. Q is the proposition that I promise I will give you $100. So that means this reads that if pigs can fly, then I promise I'll give you $100. So now you're willing to bet on this. But it turns out that they can. It's true. But then I don't give you the $100. I broke my promise. So that's what makes it false. But let's say I'm feeling generous. I'm wrong. You're right. So I guess you know what. I'll just give you the $100. This makes it true. Q is not entirely dependent on P. It can, if false then true, also gives a truth value. I could still give you the $100. And if false then false is obviously also true. If pigs can't fly, I'm not going to give you my $100. It's as simple as that. Now, the logical operation for if P, the negation of Q. Again, please make a negation column. You do not want to make a silly mistake in such an easy topic like this. Just make a negation column. So now let's fill in the values for negation of Q, which is basically just the opposite truth value. So if this is true, that gives us false over here. If this is false, that gives us true. That means this is also true, and this is false. So now, since our final logical operation focuses on P and negation of Q, we do not need to look at Q anymore. So let's compare the truth values of P and negation of Q. The same rules apply as the last slide because this is a conditional statement. It's a conditional statement. So if true then false is false. If true then true is true. If false then false is true. Again, I'm looking at the value here and the value here, the value here and the value here, and I'm comparing those. So if false then true also gives us true. Again, broken down, this is really easy. All right, now we're on to the big one. This is a problem you're definitely going to see if you're studying discrete mathematics. It's a congruency problem. What this is asking is that is this logical operation congruent to this logical operation? So that means that if we get the same truth values in this column as this column, then they are congruent. If every single truth value, oh, these are rectangles. If every single truth value just matches, then they're congruent. Now over here we have a larger set of combinations because we have a third proposition. We have the R. So we have a lot more. That's 1, 2, 3, 4, 5, 6, 7, 8. We have 8 different sets of combinations. Let's, again, like every problem, break this down. First, we want to look at P or Q. We already have the truth values for R itself. P or Q. This is true because, okay, hold on. Let me put a rectangle around this like all the other problems. We're only looking at this for P or Q. So now we have one of these has to be true. That's the case. One of these has to be true. That's the case. One of these has to be true. That's also the case for this. There's one of these. And then let's just keep going. Keep going. Okay, that's a bad T. Here we go. And the last two are false, false, and false, false. So we get false and false. Great. That's one column done. And now we're looking at these columns, comparing the truth values of those. So this itself has a truth value, and R has a truth value. True or true, that gives us true. False or true, it's an or statement, so there just has to be one true. True, this is true, that's true. This is also true, true, and the last one is false. So we only have one false at the end. All right, now for the right-hand side of the logical operation, we have to fill out a separate column for Q or R. So that means that we have to look right here, which means we are looking at these two columns now, Q or R. So again, true, 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 false, true, 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 and false. Great, now we have Q or R. So now let's look at the P column and the Q or R column. Those are the truth values that we have to compare for this last logical operation. And if this column turns out to have the same truth values as the left-hand side of the congruency, then they're actually congruent. Otherwise, they're not. So let's see if that's the case. We have true, 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 true. We have another true, 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 and the last one is false, false. All right. So now we are done with the entire truth table, but now we have to confirm that the left-hand side of the congruency and the right-hand side of the congruency have the same truth values. And it seems that that's the case because all the values are true except for the last one being false. So, this and this have the same truth values, therefore our final answer is that this is congruent. And that sums it up. Thanks for watching. Please make sure to like and subscribe, and the next video is going to be about tautologies.